Quadcopters are everywhere. Hello, my name is Kevin Craig. This presentation is on the fundamentals of quadcopters. I will cover quadcopter equations of motion derived using the Newton-Euler method and also the Lagrange method, and then control design for the quadcopter to hover and also follow a motion profile, a trajectory. Here you see a picture of the Crazy Fly quadcopter. This quadcopter is small enough to fit in the palm of your hand. Quadcopter equations of motion. A quadcopter, also known as a quadrotor, is a helicopter with 4 rotors and 6 degrees of freedom. The rotors are directed upwards, and they are placed in a square formation with equal distance from the center of mass of the quadcopter. The quadcopter is controlled by adjusting the rotational speeds of the propellers, which are spun by electric motors. The quadcopter is a typical design for small unmanned aerial vehicles, UAVs, because of the simple structure. Quadcopters are used in surveillance, search and rescue, construction inspections, and, unfortunately, warfare. Our aim is to study the physical model of the quadcopter and derive the mathematical model, that is, the equations of motion, using both Newton-Euler and Lagrange methods. We also want to develop proper methods for stabilization and trajectory control of the quadcopter. The challenge in controlling a quadcopter is that the quadcopter has 6 degrees of freedom, but there are only 4 control inputs. It is an under-actuated, nonlinear, complex system. The reference frames we will use are an inertial reference frame fixed to the surface of the Earth and a body-fixed reference frame. Both of these reference frames are Cartesian coordinate systems. There is a hierarchy of physical models possible for the physical system, the quadcopter. The physical model depends on the simplifying assumptions we make. Here, the simplifying assumptions will lead to a control-oriented model. The aircraft is assumed to be a rigid body. The propellers are assumed to be rigid. The quadcopter frame is symmetrical. The XZ and YZ planes are planes of symmetry. The mass center of the quadcopter coincides with the geometric center of the rigid frame. The mass moment of inertia of each motor rotor and attached propeller is assumed to be small and negligible. The Earth is assumed to be flat and is the inertial reference frame. Quadcopter interaction with the ground is neglected, and the sensors, the inertial measurement unit, which consists of 3 gyroscopes and 3 accelerometers, measure relative to the body-fixed axes. Reference frames. 2 frames of reference are important: the inertial reference frame and the body-fixed reference frame. We take a frame of reference attached to the surface of the Earth as the inertial reference frame, since the accelerations due to the rotation and translation of the Earth are negligible compared to the accelerations of the quadcopter. A body fixed reference frame is necessary as the aerodynamic forces act on the quadcopter body, and the inertial measurement unit sensors, the gyroscopes and accelerometers, measure quantities relative to the body fixed reference frame. The equations of motion require absolute velocities and absolute accelerations, both translational and rotational. The orientation, roll angle phi, pitch angle theta, yaw angle psi, and position, up down z, left right y, forward backward x, of the quadcopter can be controlled to desired values by changing the speeds of the four motors. The forces exerted on the quadcopter are the thrust and gravitational forces, and the moments exerted are the pitching, rolling, and yawing moments. The propellers are divided into two groups: front and back propellers, 1 and 3, representing the x-axis, and the right-left propellers, 2 and 4, representing the y-axis. In each group, there are two diametrically opposite motors with the same direction of propeller rotation. Front and rear propellers, 1 and 3, rotate counterclockwise. Right and left propellers, 2 and 4, rotate clockwise. Shown is a diagram of the quadcopter with its body-fixed reference axes. The XYZ coordinate system represents the inertial reference frame. The XB-YB-ZB coordinate system are the body-fixed reference axes. They are aligned now with the inertial reference frame. The center of the body-fixed reference axes is at the CG, center of gravity of the quadcopter frame, which is the geometric center of the quadcopter frame. There are 4 motor propellers on the quadcopter. They are numbered 1, 2, 3, and 4. Motors 1 and 3 are located along the body-fixed x-axis. The positive x direction indicates the front. The negative x direction indicates the back. These two motors rotate in the same direction in a counterclockwise direction. Motors 2 and 4 are aligned along the body-fixed y-axis. Motor 2 indicates the right direction. Motor 4 indicates the left direction. These two motors rotate in a clockwise direction. Both motor 2 and motor 4 rotate in the clockwise direction, while motors 1 and 3 rotate in the counterclockwise direction. The forces acting on the quadcopter are the weight force, mg, the mass times the acceleration due to gravity, that acts at the CG of the quadcopter, and it acts in the negative z direction, which is the z direction of the inertial reference frame. The thrust forces, and there are 4, 1 for each motor propeller, are F1, F4, F3, F2, and they are in the positive z sub b coordinate direction, the direction of the body-fixed z-axis on the quadcopter. The combination of these four forces give the quadcopter its thrust. In addition, there are four moments acting on the quadcopter, one from each motor rotor propeller combination. Here we see motor 1 rotates counterclockwise. The reaction torque or moment from the motor rotor and propeller acts in the opposite direction. This is the torque from motor 1. Similarly, motor 2 rotates in the clockwise direction. The reaction torque from the motor 2 rotor and propeller acts in the counterclockwise direction and is indicated by tau sub m2. Similarly, motor 3, which rotates in the counterclockwise direction, the reaction torque from its motor, rotor, and propeller act on the motor, on the quadcopter frame in the clockwise direction and is indicated by tau sub m3. And lastly, motor 4, which rotates in the clockwise direction, its reaction torque is indicated in the counterclockwise direction due to its rotor and propeller, and it is labeled tau sub m4. This then is a diagram that shows the body fixed reference axes and the forces and moments acting on the quadcopter frame. The quadcopter has 6 degrees of freedom, but only 4 actuators, the 4 propellers. And the 4 propellers are all pointing in the same direction, in the positive z-axis of the body fixed reference frame. How do we control the 6 degrees of freedom of the quadcopter? In the following diagrams, omega indicates motor speed and hence propeller speed, and delta indicates a speed change, either positive or negative. We control the altitude of the quadcopter, that is its motion in the positive z direction along the z-axis of the body fixed reference frame, by varying the speed of all propellers by the same amount. In this diagram, we see we have acceleration in the z direction of the body fixed reference frame by increasing the speed of all 4 motors. The quadcopter will then move in this positive z direction. We control the pitch angle of the quadcopter, which is a rotation about the y-axis of the quadcopter body fixed reference axes, by leaving the speed of motors 2 and 4 unchanged, but then by increasing the speed of motor 3 and decreasing the speed of motor 1. We see here motor 3's speed is increased, motor 1's speed is decreased, and we have a positive angular acceleration in the pitch angle theta. When we change the pitch, though, of the quadcopter will move then in the positive x direction, the positive x direction of the body fixed reference frame, x sub b. So when we control pitch, we control the orientation of the drone, its pitch angle, but we also then control the motion of the drone in its positive x direction. We control the roll angle of the quadcopter. This is a rotation about the x-axis by leaving the speed of motors 1 and 3 unchanged, but then by increasing the speed of motor 4 and decreasing the speed of motor 2. Here we see motor 4's speed is increased with a positive delta. Motor 2's speed is decreased with a negative delta. This causes a positive angular acceleration of the roll angle phi. This roll of the quadcopter will then cause the quadcopter to move in the negative y direction, as shown here. So when we control the roll angle, we are also controlling the movement of the drone in the negative y direction of the body fixed reference frame. If we want the quadcopter to rotate about its positive z-axis, which we call the yaw angle, then we must change the speeds of all four motors. And we have to understand that the direction of rotation of a motor, of a propeller, causes an opposite reaction moment on the quadcopter. The quadcopter's propellers for motors 1 and 3 rotate in the same direction, and the quadcopter's propeller speed of motors 2 and 4 rotate in the same direction, but in an opposite direction. And so if we want to have a positive yaw angle, we then need to increase the speed of motors 2 and 4, as indicated by the positive delta, and decrease the speed of motors 1 and 3. The arrows here show the increase in speed, but motors 2 and 4, by increasing their speed in the clockwise direction, will cause a torque on the quadcopter about its z-axis in the counterclockwise direction, as indicated by the yaw angle in the counterclockwise direction, which is the positive direction for the z-axis orientation of the body fixed reference frame. And since motors 1 and 3 rotate in the counterclockwise direction, which means that they impart a clockwise torque or moment to the quadcopter frame about its positive z-axis, we then need to reduce that reaction torque on the quadcopter, and so we reduce the speed of motors 1 and motor 3. This change in all four motors will give us a positive yaw angle, which is a rotation about the z-axis of the body fixed reference frame. We have stated that there are two reference frames we use to study the motion of the quadcopter. The inertial reference frame, which is a Cartesian reference frame fixed to the surface of the Earth, and a body fixed reference frame, also a Cartesian reference frame. Initially, these two reference frames are aligned, but as the quadcopter goes through its change in orientation, roll, pitch, and yaw, the body fixed coordinate system, then is misaligned with the inertial reference frame, which is fixed to the surface of the Earth. How then do we study this very complicated change in orientation of the quadcopter? We do so by using two intermediate frames of reference. I call them R1 and R2. R is the inertial reference frame. R3 is the body fixed reference frame. R1 is a rotation about the positive z-axis of the inertial reference frame, or the positive z-axis of the quadcopter, which I call B3. Initially, B1, B2, and B3 are aligned with X, Y, and Z. The first rotation I consider is what is called a yaw rotation, and it's a rotation about the B3 axis. We see the directions of B1 and B2 are then changed, and they rotate through the angle psi. Since B3 and Z maintain the same orientation throughout this yaw rotation, this then is a simple angular velocity. And the rate of change of psi, its angular velocity, is simply psi dot. This is then simple angular velocity. If I then rotate about the B2 axis of the body fixed reference frame, as shown here, which is a pitch rotation, the angle being theta, the B2 axis in reference frame R1 and the B2 axis in reference frame R2 stay parallel through this pitch rotation. And hence, the rotation from R1 to R2 about the B2 axis is also simple angular motion. And the angular velocity in the pitch angle theta is simply theta dot. So B2 in reference frame R1 and B2 in reference frame R2 stay parallel through this pitch rotation. Lastly, if I talk about rotation about the B1 axis, which is a roll axis, and the angle is phi, I see that the B1 axis in R3 and the B1 axis in R2 remain parallel during this roll motion. And so once again, I have simple angular motion in going from R2 to R3, and the angular rotation, angular velocity in roll is phi dot because of this simple angular velocity. So I can describe the final motion of the quadcopter, which has changed its orientation in yaw, pitch, and roll. I can describe it by moving from the inertial reference frame through two intermediate reference frames to the final reference frame by means of three simple angular motions, three simple angular velocities, which I can now combine in a matrix manipulation to represent the final angular motion, final angular velocity of the quadcopter with respect to the inertial reference frame. Let us now formally talk about simple angular velocity of a rigid body. When a rigid body R1 moves in reference frame R in such a way that there exists throughout some time interval a unit vector whose orientation in both R1 and R is independent of the time, then rigid body R1 is said to have simple angular velocity in R throughout this time interval. Consider this example. We have a disk rotating in a support, which also rotates with respect to the ground reference frame R. R1 is the reference frame of the support. R2 is the reference frame of the disk. The angular velocity of R1 in R is simple angular velocity because R1, its x-axis, remains parallel to the x-axis of R throughout its entire motion. So the angular velocity of R1 in R vector equals the angular velocity of R1 in R scalar times I hat, but I hat is the same as I1 hat. The unit vectors remain parallel through the motion. And if theta is the angular displacement, then theta dot is the angular speed of R1 in R, here shown as omega 1. So here, R1 has simple angular velocity in R, omega 1, and R2 has simple angular velocity in R1, shown as omega 2. But R2 does not have simple angular velocity in R. So how do we determine the angular velocity of R2 in R? We use a very powerful theorem called the addition theorem for angular velocities. The addition theorem for angular velocities. Consider multiple reference frames, R1, R2, through R sub n. The following relation applies, whether the angular velocities are simple or not. The angular velocity of R sub n in R equals the angular velocity of R1 in R plus the angular velocity of R2 in R1 plus dot 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 plus the angular velocity of R sub n in R sub n minus 1. There exists at any one instant only one angular velocity of R sub n in R. Also, note that the angular velocity of R sub n in R is the opposite of the angular velocity of R in R sub n. This addition theorem is very powerful, as it allows one to develop an expression for a complicated angular velocity, like our quadcopter, by using intermediate reference frames, real or fictitious, that have simple angular velocity relations between each of them, as we did in determining the orientation and its rate of change of the quadcopter with respect to the ground or inertial reference frame. Referring back to our example, where R2 is a disk rotating in the support R1, which rotates in the grounded reference frame R, the angular velocity of R2 in R equals the angular velocity of R1 in R plus the angular velocity of R2 in R1. The angular velocity of R1 in R is simple angular velocity. The angular velocity of R2 in R1 is simple angular velocity. But the angular velocity of R2 in R2 in R is not simple angular velocity, but it is easily calculated using the addition theorem for angular velocities, as we are doing for our quadcopter. We need to express the quadrotor absolute angular velocity in the body fixed reference frame. We need the absolute angular velocity, as that is what is required for our equations of motion. The angular velocity of the body fixed reference frame in the grounded reference frame, or the angular velocity of R3 in R, by the addition theorem for angular velocities, equals the angular velocity of R3 and R2 plus the angular velocity of R2 and R1 plus the angular velocity of R1 and R. R is our grounded reference frame. If I move from R to R1, I rotate through the yaw angle psi, and I rotate about the common z-axis, k hat equals k1 hat. When I rotate from R1 to R2, I rotate through the pitch angle theta, and I rotate about the common y-axis, j1 hat equals j2 hat. And when I rotate from R2 to R3, I rotate through the roll angle phi, and the x-axis is common. I2 hat equals I3 hat. These are all simple angular velocities. And so the angular velocity of R3 and R equals phi dot I3 hat plus theta dot J2 hat plus psi dot K1 hat. I need to express each of these unit vectors in terms of the unit vectors fixed in the body fixed reference frame. I3 hat is already in the body fixed reference frame. So J2 hat and K1 hat need to be expressed in terms of the body fixed unit vectors. How do I do this? I express each of these rotations, R to R1, R1 to R2, R2 to R3, which are each simple angular rotations. I represent them using this matrix representation. Here I relate I1 hat and J1 hat to I hat and J hat through the angle psi. The shorthand notation is C represents cosine, S represents sine. And this is simple angular motion. Similarly, when I move from R1 to R2, I rotate through the angle theta. The y-axis of both reference frames is common. J1 hat equals J2 hat. And I represent the relationship between K2 hat and I2 hat and K1 hat and I1 hat with this 2 by 2 matrix. Similarly, when I move from R2 to R3, I rotate about the common x-axis through the angle phi, and I can relate J3 hat and K3 hat to J2 hat and K2 hat through this 2 by 2 matrix. And so I can represent my absolute angular velocity, R3 and R, in terms of unit vectors fixed in the R3 reference frame, the body fixed reference frame. I3 hat is already in the R3 reference frame unit vectors. J2 hat is equal to cosine phi J3 hat minus sine phi K3 hat. And I represent that here. K1 hat is equal to cosine theta K2 hat minus sine theta I2 hat, as shown here. But I2 hat is the same as I3 hat, and K2 hat is equal to sine phi J3 hat plus cosine phi K3 hat. When I make that substitution, my final expression is shown here. The angular velocity of R3 and R, which is the absolute angular velocity of the quadcopter in the grounded reference frame, is expressed in the body fixed set of unit vectors, I3 hat, J3 hat, K3 hat, through these expressions. And I represent each of these terms by the letters P, Q, and R. Let's summarize. I want an expression that will relate the unit vectors in the body fixed axes after a change in roll, pitch, and yaw of the quadcopter. I want a relationship between those body fixed unit vectors and the unit vectors fixed in the inertial reference frame. I can combine the three matrices from the previous slide as shown below. Initially, the quadcopter's axes are aligned with the axes of the inertial reference frame. This matrix takes me from the inertial reference frame to the R1 reference frame, which is through the change in yaw. This matrix takes me from the R1 reference frame to the R2 reference frame, which is due to a change in the pitch angle theta. This matrix takes me from the R2 reference frame to the R3 reference frame through the roll angle phi. And the result is unit vectors B1, B2, B3 in the quadcopter's body fixed reference frame, and how they are related to the unit vectors I hat, J hat, and K hat in the grounded reference frame. If I multiply these three matrices together, I get this one rotation matrix, which expresses that relationship. Note that this is a rotation matrix, and a property of a rotation matrix is that its inverse is equal to its transpose. And we will make use of that property in the following analyses. I've written again the relationship between the unit vectors in the body fixed coordinate system and the unit vectors in the grounded reference frame, the inertial reference frame. And I've multiplied these three matrices together to get this one rotation matrix. And I've expressed that in shorthand form here. So here, the unit vectors in the body fixed reference frame are expressed in terms of the unit vectors in the inertial reference frame, I hat, J hat, and K hat. If I want to express the unit vectors in the grounded reference frame in terms of the unit vectors fixed in the body fixed reference frame, I need the inverse of the rotation matrix. A property of rotation matrices is that the inverse of a rotation matrix is equal to its transpose. And the transpose is obtained by simply interchanging rows and columns. This is the transpose of the rotation matrix, which is the same as the inverse of the rotation matrix. And it expresses the unit vectors in the grounded reference frame, I hat, J hat, K hat, in terms of the unit vectors in the body fixed reference frame, here identified as B1, B2, and B3. Here I express the absolute angular velocity components, omega roll, omega pitch, omega yaw, in the body fixed reference frame in terms of the angles phi and theta and the rate of change of those angles, phi dot, theta dot, and psi dot, according to my expression derived using the addition theorem for angular velocities, written here in longhand and written here in shorthand using the letters P, Q, and R. In order to obtain an expression for phi dot, theta dot, and psi dot in the inertial reference frame, I need to take the inverse of this matrix. This is not a rotation matrix, and so its inverse is not equal to its transpose. I need to formally take the inverse of this matrix, which I have done here. And so now the angles phi dot, theta dot, and psi dot in the inertial reference frame are related to the angular velocity components, the absolute angular velocity components expressed in the body fixed axes, omega roll, omega pitch, omega yaw, through this matrix, which is the inverse of the matrix shown above. Let's now talk about mass distribution. The quadcopter is assumed to have a symmetric structure with the center of gravity located at the geometric center. The XZ and YZ body fixed planes are planes of mass symmetry, and therefore the inertia matrix is a diagonal matrix. The mass moments of inertia, IXX, IYY, IZZ, are principal moments of inertia, and all the products of inertia, as shown here in the inertia matrix, are all zero. A simple model will further inform us. Here I've modeled the quadcopter as a central mass represented by the sphere mass M and four point masses, mass M with no inertial properties. And these represent the motors and propellers. The X, Y, and Z axes of the body fixed coordinate system are shown. To find the mass moment of inertia about the x-axis, the mass moment of inertia about the x-axis for a sphere is given by the expression 2/5 m, the mass of the sphere, times its radius squared. And this is the mass moment of inertia of a sphere about any axis through its CG, through its geometric center for a homogeneous solid sphere. The point masses along the x-axis do not contribute to the mass moment of inertia about the x-axis, but through the parallel axis theorem, the point masses along the y-axis, and there are two, contribute to the mass moment of inertia about the x-axis by the expression m, its mass, times this distance, which is expressed as L, squared. And so the mass moment of inertia of this system of a central sphere and symmetrically placed four point masses is given by IXX equals 2/5 mr squared plus 2 times small m L squared. And this is the same for the y-axis. The mass moment of inertia about the y-axis is the same expression because the point masses along the y-axis do not contribute to the mass moment of inertia about the y-axis, but the point masses along the x-axis do contribute. And so the expression is identical. The mass moment of inertia about the y-axis equals the mass moment of inertia of the sphere about the y-axis, which is 2/5 mr squared, plus the contributions of the two point masses on the x-axis, which is ml squared multiplied by 2, since there are 2 point masses. Now the mass moment of inertia about the z-axis for the sphere is the same expression, 2/5 mr squared, but all four point masses contribute to the mass moment of inertia about the body fixed z-axis. And the contribution of each is ml squared. And so I have 4 times ml squared, again, by the parallel axis theorem. Because of symmetry, all of my products of inertia are 0. This is a diagonal matrix, and the mass moments of inertia, IXX, IYY, IZZ, are then principal moments of inertia. As a sample, a drone would have a mass of this order of magnitude with mass moments of inertia given by these values, just to illustrate the order of magnitude of the mass and mass moments of inertia of a drone similar to our Crazy Fly quadcopter. How can I obtain experimentally the mass moments of inertia of my quadcopter? I will use a technique called the bifilar pendulum to experimentally determine IX, IY, and IZ of the quadcopter. I have an object, any object of weight W, that I wish to find the mass moment of inertia for about an axis, a vertical axis, through the CG of the object. I suspend the object using 2 strings parallel to each other and parallel to the z-axis through the CG of the object, a distance a from the CG of the object. The length of the strings is L. If I twist this object through a small angle, there will be a restoring force from the strings. I assume that the tensile force of the ropes or strings will not change, and so this restoring force, F, will remain constant. I'll also neglect any damping in this system, any energy dissipation in the system. And so this system is an example of a rigid body in fixed axis rotation about an axis through the CG in the vertical direction. There is a restoring moment due to the force in the strings. From the geometry, I see that the component of the force, again, in the plane of the object, is F sine phi. And that force has a moment arm equal to the length A. And so the restoring moment for one string is F sine phi times A, but there are 2 strings, and so I have the multiplier 2, and the minus sign means that this is a restoring moment. My equation of motion then is J theta double dot equals minus 2 Fa sine phi. From the geometry, and for small angles phi and theta, I can write that L times phi equals A times theta. I can solve for phi equal to A theta over L, and I can substitute into this expression. So my equation of motion then becomes J theta double dot equals minus 2 Fa sine of A theta over L. And for small angles, the sign of this expression equals that expression. And so my equation of motion then reduces to J theta double dot equals minus 2 Fa squared theta over L, or written out in this form, equal to theta double dot plus 2 Fa squared over JL times theta equals 0. Remember, J is the mass moment of inertia of the object about a z-axis, a vertical axis through the CG. And F is the force in the strings, which is equal to the weight of the object divided by 2. Since this is an ordinary differential equation, a second-order ordinary differential equation with constant coefficients, I know from my study of differential equations that this expression then is the natural frequency of vibration of this system, natural frequency of oscillation. And this is in radians per second. And so I can, and this expression is the actual square of the natural frequency in radians per second. So 2FA squared over JL is equal to the square of the natural frequency in radians per second. And therefore, the natural frequency in hertz, and I multiply radians per second by 1 over 2 pi, where 2 pi is radians per cycle, I get a frequency in cycles per second. So if I can measure time the oscillations with a stopwatch and get an expression for the frequency in cycles per second, I then can solve for J as I know everything else in this expression. I know that F is equal to W over 2. I know A, I know L. I've measured F in cycles per second. I can then solve for J, which is the mass moment of inertia of this object about the z-axis through the CG. And I will do this for the quadcopter to find IX, IY, and IZ. We first use the Newton-Euler approach to obtain the equations of motion for the quadcopter. The Newton-Euler approach first requires that we draw a free body diagram of the quadcopter and show all the external forces acting on the quadcopter. And these are forces of contact or forces that act at a distance, such as gravity, weight, or electromagnetic forces, which here we do not have. Once I've drawn the free body diagram, I then draw an effect diagram on which I show the inertia force, mass, times the absolute acceleration of the CG. That's the absolute acceleration with respect to the grounded reference frame. And then the time rate of change of the absolute angular momentum of the quadcopter with respect to the grounded reference frame. And this is the absolute angular momentum with respect to the CG, the center of gravity of the quadcopter. The equations of motion, which are expressed here in diagram form, written out, say that the summation of all the external forces, both contact and at a distance, acting on the quadcopter, equals the time rate of change in the grounded reference frame of the absolute linear momentum of the quadcopter. And since the mass of the quadcopter does not change, it is constant, this equals the mass of the quadcopter times the derivative in the grounded reference frame of the velocity of the center of mass of the quadcopter in the grounded reference frame, or the absolute velocity of the center of mass of the quadcopter. The moment equation says that the summation of moments of all the external forces acting on the quadcopter about the center of mass, this is m over bar, and it's a vector, equals the time rate of change in the grounded reference frame of the absolute angular momentum of the quadcopter with respect to the center of mass. This is an H with an overbar. These are the Newton-Euler equations, both in diagram form and in equation form, and we will now apply these equations to our quadcopter. Let's now find the absolute angular momentum of the quadcopter with respect to its center of gravity, its CG. Here is the absolute angular momentum. This is the angular momentum with respect to the grounded reference frame, R. And it's the angular momentum of the quadcopter, R3, with respect to its CG as indicated by the overbar. And these are the components of that in the body fixed coordinate frame, x3, y3, z3. And this is defined and equal to the inertia matrix. And this is the inertia matrix with respect to body fixed axes. Why do we use this? Because these terms, these expressions for the mass moments of inertia are constant in the body fixed reference frame and do not change with time. And this matrix is multiplied then by the absolute angular velocity components of the quadcopter. So these are the components of the angular velocity in the R reference frame. And these are the components in the body fixed axes, x3, y3, z3. And these are the angular velocity components of the quadcopter, the R3 reference frame. If I make a substitution for these three components, I get the matrix shown here. This angular velocity of the quadcopter in the grounded reference frame, its body fixed axes components, P, Q, and R, are shown here, P, Q, and R. In what follows, we will be using the chain rule. So as a refresher, let me define what that is. Let x1, x2, xn be variables that depend on time t in an unknown manner. Also let the function f be a function of x1, x2, x sub n, be some function of these variables. The total time derivative of the function f, or df dt, is a finite quantity, and according to the chain rule of differentiation, is given by the following expression. df dt equals the partial derivative of f with respect to x1 times dx1 dt, plus, and so forth through the remaining terms, to the partial derivative of f with respect to x sub n times dx sub n dt. To write the equations of motion for the quadcopter, we need to know the forces and moments acting on the quadcopter from the environment. The first force is the thrust force, T. Its magnitude is equal to K, which is a lift factor determined experimentally, times the sum of the squares of the speeds of the four propellers. And the propeller speed is expressed in radians per second. The thrust vector is in the direction of the B3 hat unit vector, which is part of the body fixed reference frame. A second force is the weight. The magnitude of the weight is its mass, the mass of the quadcopter, times the acceleration due to gravity. The direction of the weight vector is in the minus k hat direction, where the k hat direction is part of the inertial reference frame. There are three moments acting on the quadcopter: the roll moment, the pitch moment, and the yaw moment. B is a drag factor. and L is the distance between any of the four rotors and the CG. Due to symmetry, that distance is the same for all four rotors. The roll moment, tau phi, a vector, is equal to the L length times the K, the lift factor, times the difference in the squares of the speeds of motor 4 and motor 2. And the unit vector is the B1 hat unit vector, part of the body fixed reference frame. The pitch moment, tau sub theta, the vector, is equal to L, the length, distance between the rotor and the CG, and the lift factor, and the difference between the squares of the speeds of motor 3 and motor 1. And the unit vector is in the B2 hat direction, which is part of the body fixed reference frame. The yaw moment, tau sub psi, is equal to B, the drag factor, times the expression, the sum of the squares of the speeds of motors 2 and 4, minus the sum of the squares of the speeds of motors 1 and 3. These are the forces and moments acting on the quadcopter from the environment. To continue our derivation of the equations of motion, we will need to understand the differentiation of a vector in two reference frames. If R and R1, R is the grounded reference frame, R1 is the reference frame attached to the rigid body. If R and R1 are any two reference frames, the first time derivatives of any vector beta, and beta is a vector not fixed in either R or R1, the first time derivatives of this vector beta in R and in R1 are related to each other as follows. The derivative of the vector beta in the R reference frame is equal to the derivative of the vector beta in the R1 reference frame plus the vector cross product of the angular velocity of R1 in R crossed with the vector beta. This is a very important relationship, and we will use it in our further derivation of the equations of motion. The translational equations of motion are given by this expression. The summation of all the external forces acting on the quadcopter from the environment, and these are contact forces and forces that act at a distance, equals the derivative in the inertial reference frame R of the absolute linear momentum of the quadcopter. And since the mass of the quadcopter is constant, that equals the mass times the derivative in the inertial reference frame of the absolute velocity of the center of mass. That's the velocity of the center of mass of the quadcopter in the grounded or inertial reference frame. I express that absolute velocity in terms of the body fixed axes with components u, v, and w. And the unit vectors are unit vectors in the body fixed reference frame. The derivative in the R reference frame of this absolute velocity of the CG is equal to the derivative of the absolute velocity of the CG in the R3 reference frame, the body fixed reference frame, plus the absolute angular velocity of the quadcopter in the R reference frame, crossed with, that's the vector cross product, the absolute velocity of the CG, that's the velocity of the CG in the R reference frame. And here I'm using the relationship of the derivatives in two different reference frames, the R reference frame and the R3 reference frame. If I substitute in for this first term the absolute velocity of the CG, which is this expression, I note that I3 hat, J3 hat, K3 hat are fixed in the R3 reference frame. So they have no derivatives in the R3 reference frame. And so this derivative is equal to U dot I3 hat plus V dot J3 hat plus W dot K3 hat. Then I substitute in for the absolute velocity of the quadcopter. It's the angular velocity of R3 and R. And I cross that with a vector cross product of the absolute velocity of the CG in the grounded reference frame. So here's the angular velocity of R3 and R expressed in the unit vectors of the body fixed axes, crossed with the absolute velocity of the CG expressed in the body fixed coordinate system. If I then execute the mathematics by taking the cross product and then gather terms together, I see that the absolute velocity of the CG in the R reference frame is given by this expression, where these are the I3 hat, J3 hat, and K3 hat components of that absolute velocity. I've previously defined P, Q, and R. The summation of all the external forces acting on the quadcopter from the environment is equal to the thrust, and that vector is in the K3 hat direction, which is the Z component of the body fixed axes, minus the weight, mass times acceleration due to gravity, and that is in the Z direction, the minus Z direction of the inertial reference frame. I need to express the K hat unit vector in the inertial reference frame in terms of the unit vectors of the body fixed coordinate system. I know that K hat equals K1 hat, and K1 hat can be expressed in terms of K2 hat and I2 hat, and that can be expressed in terms of I3 hat, J3 hat, and K3 hat. So the weight vector is minus mg times this vector. Putting this all together, I then get my three equations, translational equations of motion for the quadcopter. To obtain the rotational equations of motion, I need to write an expression for the summation of the external moments acting on the quadcopter. Those moments are moments due to roll, pitch, and yaw. And we've already written expressions for these moments. I need to take the derivative of the absolute angular momentum in the R reference frame. And I know that that's equal to the derivative of the absolute angular momentum in the body fixed reference frame, the R3 reference frame, plus the absolute angular velocity of the quadcopter. That's the angular velocity of the R3 reference frame in the grounded or R reference frame, vector cross product with the absolute angular momentum with respect to the CG of the quadcopter. That's H bar. H bar can be written by the following expression. These are the components in the body fixed axes. I3 hat, J3 hat, K3 hat, and these are the expressions P, Q, and R. as shown in the next line of my equation. If I take the derivative of this expression in the R3 reference frame, the body fixed reference frame, the unit vectors are fixed in that reference frame, as are the mass moments of inertia, I bar x3, I bar y3, I bar z3. And so this derivative is made up of the following terms, with a p dot, a q dot, and an r dot. I then expand those derivatives, and my expression for p dot, q dot, and r dot is shown here in these expressions. I then need to take the cross product of the angular velocity of the quadcopter in the grounded reference frame and cross that with the absolute angular momentum of the quadcopter with respect to its CG. This is the expression for the absolute angular velocity, and this is the expression for the absolute angular momentum with respect to the CG. If I take the cross product, the result is shown here. This vector cross product can be rewritten in simplified form as shown here. If I put all of this together, my equations, the rotational equations of motion, equations 4, 5, and 6, are shown here. These are the rotational equations of motion for the quadcopter. Let's summarize. The Newton-Euler equations of motion are given by the following. I define P, Q, and R by these expressions. My constants are the mass, m, g, the length, L, the factors B and K, and the mass moments of inertia about the CG in the body fixed reference frame, x3, y3, z3. These are all constants. Equations 1, 2, and 3 are my translational equations of motion. Equations 4, 5, and 6 are my rotational equations of motion. And the thrust T is defined by this expression here. This is the Newton-Euler approach to deriving the equations of motion. Let's now use the Lagrange method to derive the equations of motion for the quadcopter. The advantages of the Lagrange method are as follows. The system of particles and rigid bodies is considered as a whole rather than being separated into its individual components. Problems are formulated in terms of kinetic energy and work, both of which are scalar quantities. Forces of constraint that do not perform work are not included. If constraint forces are required, apply the Newton-Euler equation or use Lagrange multipliers. The use of generalized coordinates instead of physical coordinates affords ease and makes the formulation versatile. What are generalized coordinates? Generalized coordinates are a set of coordinates which describe general motion and recognize constraint. A set of coordinates is called independent when all but one of the coordinates are fixed. There remains a range of values for that one coordinate, which corresponds to a range of admissible configurations. A set of coordinates is called complete if their values corresponding to an arbitrary admissible configuration of the system are sufficient to locate all parts of the system. Generalized coordinates are complete and independent. We will use the Lagrange formulation for holonomic systems. What are holonomic constraints? Consider a system described by n generalized coordinates q1 through qn. Suppose that there are m constraint equations of the form f sub I, a function of q1 through qn, and also time, equals 0. I is equal to 1 to m. Constraints of this form are known as holonomic constraints. In theory, one could use these equations to solve for m coordinates in terms of the n minus m remaining coordinates in time, thereby retaining only as many generalized coordinates as there are degrees of freedom. Lagrange's equations for holonomic systems is stated as follows. The derivative with respect to time of the partial derivative of t, which is the kinetic energy of the system, the partial derivative of t with respect to qi dot, where qi is a generalized coordinate, minus the partial derivative of t with respect to qi equals capital Q sub I, where capital Q sub I is the generalized force in the direction of the ith coordinate. As we mentioned, small q sub I are the generalized coordinates, and T is the kinetic energy of the system. For conservative forces, for example, gravitational and elastic, the force F equals minus the gradient of the scalar function V, where V is the potential function, that is a function of the generalized coordinates. So the force F equals minus the gradient of the potential function V. In that case, the generalized force in the direction of the ith coordinate is minus the partial derivative of the potential function V with respect to the generalized coordinate q sub I. And so the Lagrange equation for holonomic systems is written in a form that we most often use, which says that the derivative with respect to time of the partial derivative of the kinetic energy of the system with respect to the derivative of the generalized coordinate minus the partial derivative of the kinetic energy with respect to the generalized coordinate plus the partial derivative of v, the potential function, with respect to the generalized coordinate equals q sub I non-conservative. So q non-conservative sub I is the generalized force in the ith coordinate direction contributed by non-conservative impressed forces only. Let's now apply the Lagrange method to the quadcopter. The generalized coordinates for the quadcopter are the position of the center of mass, x, y, z, and the angles of roll, pitch, and yaw, phi, theta, and psi. These give the absolute position and absolute orientation. The kinetic energy of a rigid body in 3 dimensions with, in this case, 6 degrees of freedom is equal to 1/2 the mass times the velocity of the center of mass squared plus 1/2 the quantity I bar x omega x squared plus I bar y omega y squared plus I bar z omega z squared plus 1/2 I bar xy omega x omega y plus 1/2 I bar YZ, omega Y, omega Z, plus 1/2 I bar ZX, omega Z, omega X. But all products of inertia for the symmetric quadcopter are 0. So I bar XY, I bar YZ, I bar ZX are 0, and I bar X and I bar Y and I bar Z are the mass moments of inertia, and hence are the principal moments of inertia. Omega X, omega Y, omega Z are the absolute angular velocities of the quadcopter. These are the X, Y, and Z components of the angular velocity. And that's absolute with respect to the ground reference frame, the inertial reference frame. As V bar is also the velocity of the center of mass with respect to the inertial reference frame. So the expression then for the kinetic energy is given by this expression, with all of the products of inertia equal to 0. What is V bar? V bar, the vector equation, is given by this expression in terms of the unit vectors of the body fixed coordinate system. But U, V, and W are components, again, in the body fixed reference system, but V bar is the velocity of the center of mass with respect to the grounded reference frame, the inertial reference frame. It's the absolute velocity of the CG. Similarly, the absolute angular velocity of the quadcopter is given by this expression. This is the angular velocity of the quadcopter, the R3 reference frame, in the R reference frame, the ground or inertial reference frame. It is written in terms of the unit vectors I bar 3, J bar 3, K bar 3 of the body fixed reference system, and those components are P, Q, and R. P, Q, and R are shown here. These are the definitions. And U is X dot, V is Y dot, W is Z dot in the expression for the absolute velocity of the center of mass. The expression for the kinetic energy of the quadcopter T is shown here. The potential energy function V is equal to mg, the weight of the quadcopter, times Z bar, which is the height of the CG of the quadcopter above the ground in the inertial reference frame. This is the Lagrange formulation that we will apply to the quadcopter, and we apply it here to the generalized coordinates X, Y, and Z. The generalized non-conservative force for the X coordinate is 0. The generalized non-conservative force for the Y generalized coordinate is 0. But the generalized non-conservative force for the Z generalized coordinate is equal to the thrust, and the thrust is in the K3 hat direction, which is the Z direction in the body fixed reference frame. Here is the thrust vector, and the thrust vector is in the K3 hat direction, which is the Z direction in the body fixed reference frame. I need to express this in terms of the unit vectors in the inertial reference frame, where the generalized coordinates X, Y, and Z are. So I replace K3 hat with unit vectors J2 hat and K2 hat. And then I replace these unit vectors with unit vectors J1 hat, K1 hat, and I1 hat. I now can represent the J1 hat, K1 hat, and I1 hat unit vectors in terms of unit vectors I hat, J hat, and K hat, which are the unit vectors in the inertial reference frame. I then simplify this expression, and I have my thrust vector with the I hat, J hat, and K hat components, and the components are shown here in the parentheses for I hat, J hat, and K hat. If I now combine this with the results of my application of the Lagrange formulation, my translational equations of motion for the quadcopter are shown here as equations 1, 2, and 3. And these are identical to what I found using the Newton-Euler method. Here I derive the equations of motion for orientation, where the generalized coordinates are roll, pitch, and yaw, phi, theta, and psi. Here, the generalized coordinate Q4 is the roll coordinate phi, and applying the Lagrange formulation for that generalized coordinate, the results are shown here. These are the terms in the Lagrange formulation. The non-conservative generalized, in this case, moment associated with the generalized coordinate phi is given by this moment, which is the moment associated with the roll coordinate phi. And this is the moment equation. I next apply the Lagrange formulation to the generalized coordinate theta, which is the pitch generalized coordinate. The terms in the Lagrange formulation are shown derived here, and the non-conservative generalized moment associated with the generalized coordinate theta is given by this expression, which is the pitch moment. Lastly, I apply the Lagrange formulation for the sixth generalized coordinate, which is the yaw coordinate psi, and here are the terms in the Lagrange formulation. The generalized non-conservative moment associated with the yaw generalized coordinate psi is the yaw moment, shown here. The results of the Lagrange analysis for the rotational equations of motion are summarized here. The three equations of motion can be represented by this matrix equation, where eta are the three rotational generalized coordinates, phi, theta, and psi. J is a 3 by 3 matrix whose elements are shown here. C is a 3 by 3 matrix whose elements are shown here. B is the input vector to the equations. It consists of the moments, the roll moment, the pitch moment, and the yaw moment. It is a column vector, a 3 by 1 matrix. So here are the three equations for the rotational generalized coordinates resulting from the Lagrange analysis. I now solve the 6 nonlinear equations of motion for the quadcopter using MATLAB Simulink. This simulation is entitled Quadcopter Roll, Pitch, Yaw, Orientation, and Altitude Proportional Derivative Control. The 6 equations, the 6 nonlinear equations of motion, are embedded in this MATLAB function block, as are the proportional derivative control algorithms for roll, pitch, and yaw, as well as for z altitude. Let's take a look at what's in this MATLAB function block. The MATLAB function block consists of the following. The inputs are the generalized coordinates and their derivatives, phi, phi dot, theta, theta dot, psi, psi dot, z, z dot, x, x dot, y, and y dot. The output from the function are the angular variables, roll, pitch, and yaw, phi, theta, and psi. W is a vector of the propeller speeds, and x, y, and z are the angular accelerations of the generalized coordinates x, y, and z. The quadcopter parameters in SI units are the mass moments of inertia, the mass, the distance from each of the rotors to the CG, the acceleration due to gravity, the lift factor and drag factor, and the 3 coefficients for drag in the x, y, and z directions. These are forces that are proportional to the speed of the quadcopter in the x, y, and z directions, and so represent what we call viscous drag, or drag proportional in a linear way to the velocities, x dot, y dot, and z dot. The proportional derivative control gains are shown here. Here are the derivative and proportional control gains for the altitude z PD controller. And here are the derivative control gains for the 3 angular controllers, phi, theta, and psi. And here are the 3 proportional control gains for the 3 angles, phi, theta, and psi. The roll, pitch, and yaw position and rate commands are all 0, as we want to bring the quadcopter to a 0 orientation from an initial configuration where the 3 angles, roll, pitch, and yaw, are 10 degrees with 0 rates of change of the 3 angles. And the altitude is equal to 1, and it's desired to bring the altitude, the quadcopter, back to the ground level. So these are the roll, pitch, and yaw, position, and rate commands, and they are all 0. The roll, pitch, and yaw torques for phi, theta, and psi are shown here. They are the outputs of the phi, theta, and psi PD controllers. The thrust T is the output of the altitude PD controller. W1, 2, 3, and 4 are the propeller speeds. J is the 3x3 matrix, which multiplies eta double dot, which is the angular acceleration of the three orientation generalized coordinates. C is the 3 by 3 matrix that multiplies the eta dot, the derivative of the three orientation generalized coordinates. And I initially set them to 0 to define the size of the matrices J and C. The elements now, the 9 elements in the J matrix, are given here. Again, the J value for the first row, first column is equal to IX, and so forth through the 9 elements of the J 3 by 3 matrix. The elements in the 3 by 3 C matrix are shown here. The B column vector consists of the 3 moments, roll, pitch, and yaw moments. The column vector N consists of the elements phi dot, theta dot, psi dot. The vector W consists of the propeller speeds W1, W2, W3, and W4. The angular acceleration of the three translational coordinates Z double dot, X double dot, and Y double dot are given by these three expressions. These are then integrated once and then twice to give me the positions X, Y, and Z. I define capital X to be X double dot, capital Y to be Y double dot, capital Z to be Z double dot. The output then is equal to the solution of the three rotational equations of motion. Eta double dot is equal to the inverse of the matrix J times the matrix B, which is a column vector of the moments for roll, pitch, and yaw, minus the C 3 by 3 matrix times eta dot, which is the N vector consisting of the derivatives of the three orientation variables, phi, theta, and psi. So here the output is the inverse of the J matrix times the matrix B minus C times N. And I've also included in the output the column vector B, which is the column vector of the three moments, tau phi, tau theta, tau psi. This then completes the statements in the matrix function, the MATLAB function. The results of the simulation are shown in the following three graphs. Here we plot the motion of the center of mass of the quadcopter in the X, Y, and Z directions. Only the Z direction, the Z motion, is under proportional derivative control. It starts at 1 and over a period of 6 seconds approaches ground, which is 0, which is what it's commanded to do. However, the X and Y motions are not under control, and they vary from a starting point of 0 to some final equilibrium point, which is not 0. To have the drone follow a certain trajectory, the X and Y coordinates need to be under control. This graph shows the roll, pitch, and yaw angles in radians. The starting point, the initial condition for the three angles is 10 degrees, shown here in radians, and the final position, desired position, under PD control is 0 degrees, and you see that all three angles reach 0 degrees in the 6 seconds of the simulation. This is the transient response for the orientation angles, roll, pitch, and yaw. And lastly, the propeller speeds are shown here for the four propellers, W1, W2, W3, and W4. And you can see where they all start. These speeds are in radians per second, and they can be converted to RPMs. And you can see that all four propeller speeds converge on one common propeller speed, which will keep the quadcopter level at essentially zero altitude, just hovering above the ground. We saw in the previous simulation, in keeping the quadcopter in a proper orientation, level with the ground, that it drifted in the X and Y direction. The altitude was controlled, but the X and Y motion was not controlled. Let's now address the issue of trajectory control, and we'll work to have the drone track a square trajectory in XY space. The purpose of trajectory control is to move the quadcopter from the original location to the desired location by controlling the rotor velocities of the quadcopter. Finding the optimal trajectory for a quadcopter is a difficult task because of complex dynamics. However, a simple control method could control the quadcopter adequately. Thus, a heuristic approach is studied and developed here. Here, zeta are the X, Y, and Z coordinates of the quadcopter. Eta are the angles for roll, pitch, and yaw. Phi, theta, psi. When we specify the propeller speeds, we then are specifying the torques for roll, pitch, and yaw, but also the thrust of the quadcopter. The roll, pitch, and yaw torques will cause the angular accelerations, eta double dot, angular accelerations for roll, pitch, and yaw, and these can be integrated with velocity and position information. So integrating the angular accelerations will give you the angular velocities. Integrating the angular velocities will give you the angles, roll, pitch, and yaw. These angles are then determined, along with the thrust, the translational linear accelerations, zeta double dot, or x double dot, y double dot, z double dot. And these then can be integrated with information from the linear velocity and can be integrated to get the linear velocity and then integrated again to get position, x, y, and z. So we see that this is a very complex, interdependent system. How then can we have the quadcopter follow a desired trajectory when we have this kind of interdependence among all of the variables of the quadcopter, and the fact that the quadcopter is an under-actuated complex system. That's our challenge. Here is the diagram again showing the interdependence among the system variables. The given control inputs, omega I, define the total thrust T and the torques for roll, pitch, and yaw. The torques affect the angular accelerations depending on the current angles and the current angular velocities. The angles eta can be integrated from the angular velocities eta dot, which are integrated from the angular accelerations eta double dot. The linear accelerations zeta double dot depend on the total thrust T and the angles eta and the linear velocity zeta dot. The linear position zeta is integrated from the linear acceleration zeta double dot through the linear velocity zeta dot. Hence, to find the proper control inputs omega I for the given states zeta, x, y, and z, this line of thought has to be done in reverse. The challenge is to generate linear accelerations which accomplish the desired trajectories according to the positions x, y, z for each time t. The translational equations of motion are shown: mx double dot, my double dot, mz double dot. I can put these three equations in matrix form. Here we have a column vector, a 3 by 1 column vector of the linear accelerations, and this equals minus g times this column vector plus the thrust divided by m times this column vector 3 by 1 matrix minus 1 over m times the diagonal matrix 3 by 3 with coefficients, drag force coefficients, a sub x, a sub y, a sub z along the diagonal. This 3 by 3 matrix multiplying the 3 by 1 column vector of velocities. This then is the equations, translational equations of motion in matrix form. I can solve for the thrust T by simply bringing the minus g times this column vector to the other side, the minus 1 over m times the diagonal matrix of drag force coefficients, multiplying the column vector of velocities to the other side of the equation, multiplying through by m, and then multiplying that by the transpose of this matrix R. The result is then shown here. And here I'm solving for the thrust T. So in this equation, eta double dot, eta dot, and psi are desired trajectory values. X double dot, y double dot, z double dot, x dot, y dot, z dot, and the yaw angle psi are desired trajectory values. And angles phi and theta and total thrust T are unknown values to be solved. I've rewritten the equations of motion, the translational equations of motion, including the drag coefficients a sub x, a sub y, a sub z. I define d sub x, d sub y, d sub z as shown. The equations of motion then can be rewritten as shown below. D sub x equals, d sub y equals, d sub z plus g equals. I will assume that the yaw angle psi is 0 degrees as we want to maintain that angle at 0 degrees so that the x direction is maintained constant. D sub x, d sub y, d sub z plus g, then reduced to these following three expressions. If in the first expression I solve for sine theta, the result is shown here. In the last expression, if I solve for cosine theta, the result is shown here. If I place sine theta over cosine theta, I get the tangent of theta. And I can solve for theta as the arctangent of dx, d sub x, divided by d sub z plus g. I can solve for the sine of phi in expression 2, and I can solve for cosine of phi from the first expression, but also from the third expression. If I place sine of phi over cosine of phi, I get the tangent of phi, as shown here. The tangent of phi is given by this expression, and phi is then the arctangent of minus d sub y cosine theta divided by d sub z plus g. So once I know theta, I can solve for phi. Another useful result is obtained by squaring dx, squaring dy, squaring the quantity d sub z plus g, and adding them together. If I add them together, I get t squared over m squared times this expression. This expression can be simplified and eventually equals 1. So T, the thrust, is equal to m times the quantity d sub x squared plus d sub y squared plus the quantity d sub z plus g squared. That sum with the square root taken. That then is equal to the thrust T. I can obtain additional useful expressions by remembering that the thrust T is given by the lift factor times the sum of the squares of the propeller speeds. And the moments in roll, pitch, and yaw are given by these expressions in the direction shown. K is the lift factor, B is the drag factor, L is the distance between the motor and the CG of the quadcopter, and that is the same for all four motors. Using these four expressions, I can solve for the propeller speeds, omega sub 1 squared, omega sub 2 squared, omega sub 3 squared, omega sub 4 squared. Let's now summarize and develop the control design for trajectory following. The forces and moments acting on the quadcopter are the thrust T, given by this expression, where omega sub I are the propeller speeds, K is the lift factor, and the thrust vector is in the B3 hat direction. The weight is equal to mg, and its direction is in the minus k hat direction. The roll moment, pitch moment, yaw moment are given here as shown, where L is the distance between the rotor and the CG, and it's the same for all four propellers, and B is the drag factor. The translational equations of motion are given by these three expressions, where A sub x, A sub y, A sub z are drag force coefficients. The rotational equations of motion are given by this equation, where eta is the column vector of the angles for roll, pitch, and yaw, and B is a column vector with the elements, the moments for roll, pitch, and yaw. Tau sub phi, tau sub theta, tau sub psi. Eta is the column vector of our angular positions. Eta double dot, the angular accelerations. Eta dot, the angular velocities. J is a 3 by 3 matrix. C is a 3 by 3 matrix. And B, as you see, is a column vector. To solve for eta double dot, I bring the C times eta dot to the other side of the equation, and I pre-multiply both sides by the inverse of J. I can then solve for eta double dot, and if I integrate once, I get eta dot, and if I integrate again, I get eta. These are the rotational equations of motion. Here are the three rotational equations of motion written again. Eta are my orientation angles, phi, theta, psi. B represents the column vector of inputs, the moments for roll, pitch, and yaw. Eta double dot are the angular accelerations. Eta dot are the angular velocities. And the J matrix is given by this matrix here. This is the matrix, the 3 by 3 matrix that's multiplying the 3 by 1 column vector of angular accelerations. The C matrix depends on eta and eta dot. It is a 3 by 3 matrix, and the 9 elements are shown here. And these were derived in both the Newton-Euler method and the Lagrange method. The control design for trajectory following is as follows. Assume that the yaw angle psi is 0 degrees. X sub d, y sub d, z sub d are the desired trajectory to follow. I will neglect air drag initially. The translational equations of motion then reduce to the following three expressions, and they can be combined to determine what the thrust T is. If I specify x sub d double dot, y sub d double dot, and z sub d double dot, and I equate those to the expressions on the right side of my equations of motion, I can then solve for the desired angle theta and the desired angle phi for my specified trajectory. Shown is the quadcopter control block diagram. The input is the desired motion profile, x sub d, y sub d, z sub d. It is inputted to a summing junction and compared to the actual values of zeta, x, y, and z. The error, or the difference between those values, is sent to a PD control block. There are three PD control algorithms. The outputs are U1, U2, and U3. U3 is augmented with the weight, mg. If I square each of these terms, U1 squared, U2 squared, and U3 plus mg squared, add them together, take the square root, I get the result as the thrust for the quadcopter T. If I take U1, U2, and U3, I can substitute them into these expressions for the desired value for theta and the desired value for phi. The desired value for psi is 0 degrees. So now I have the desired angles theta sub d, phi sub d, and psi sub d. I can then input those three angles into a summing junction, compare them to the actual values of my angles roll, pitch, and yaw, eta. Based on that difference, I substitute them in to a PD control block where there are 3 PD control algorithms. These are multiplied by their respective mass moments of inertia, Ix, Iy, Iz. The result are the moments for roll, pitch, and yaw, tau sub phi, tau sub theta, tau sub psi. These then are substituted along with the thrust T into these four expressions where the propeller speeds can be calculated. The output is then omega sub I squared. Omega sub I squared, those four values can be summed, multiplied by K, the lift factor, which results in the thrust T. The thrust T can be multiplied by 1 over m, and along with the input of the angles eta, roll, pitch, and yaw, using these expressions, I can solve for x double dot, y double dot, z double dot. These then are the outputs of this block, and they can be integrated once to get the linear velocity, eta dot, and integrated again to get eta. And you see that eta dot needs to be fed back into these equations in order for that integration, in order for x double dot, y double dot, and z double dot to be solved for. These then are the values for x, y, and z, which are then compared to the desired values of x, y, and z, x sub d, y sub d, z sub d in this summing junction. Knowing the four speeds of the propellers, I can then determine what the moments are for roll, pitch, and yaw. The output of this block is then the moments for roll, pitch, and yaw. These then can be substituted in to my differential equation for the angles eta. The output of this block is then eta double dot, which are the angular accelerations for roll, pitch, and yaw, which then can be integrated once to give me eta dot, and integrated again to give me eta. And eta dot is fed back into this block in order to then solve these equations. The output is then eta, which are the values for roll, pitch, and yaw, which are then compared to the desired values for roll, pitch, and yaw in this summing junction. This then is the complete quadcopter control block diagram. This control design is implemented in MATLAB Simulink. Here is my desired square trajectory. This is the translational controller. This is the rotational controller. This is a subsystem that relates the thrust and angle moments, roll, pitch, and yaw moments, to the propeller speeds. This block represents the translational dynamics, and this block represents the rotational dynamics. And the quadcopter parameters used in this simulation are shown here. The result of the Simulink simulation is shown here. This is the quadcopter tracking a square trajectory as shown by the red line. The blue line shows the actual response of the quadcopter to that square trajectory command. This graph shows the Z altitude during the XY square trajectory profile tracking. The z-coordinate initial value is 2, and the final value is 6. And you can see the response to the PD control of altitude, the initial movement to the final desired altitude of 6, and you can see the perturbation at each corner in our square trajectory, as expected. In summary, the equations of motion for a quadcopter were derived using the Newton-Euler and Lagrange approaches. A control system was designed and a computer simulation created to ascend to a specified altitude, hover, and then return. Proportional derivative control was used for both orientation and vertical motion. A control system was designed and a computer simulation created to have the quadcopter track a square motion profile in the XY plane. Proportional derivative control with a heuristic approach was used to control the trajectory. This approach is dependent on system parameter values. This concludes the presentation. Thank you for your attention. MATLAB files are attached to this presentation. The files are the quadcopter parameter file, the quadcopter orientation Simulink file, and the quadcopter tracking Simulink file.